The molecule N2O is a gas that has two well-known uses or roles in our lives. Its first role is as an anesthetic that is also called laughing gas, and it has another role, which is that of a greenhouse gas. Now, it's a greenhouse gas because it can undergo certain reactions and turn into molecules that sort of deplete the ozone layer and contribute to global warming, etc., etc. I'm not really going to get into the science of that right now. N2O can undergo a reaction, which actually renders it much less of a greenhouse gas. And that reaction is the decomposition reaction of N2O into nitrogen gas and oxygen gas. Now, the reason that this reduces sort of the greenhouse gas effect of N2O is that nitrogen and oxygen are the two main components of our atmosphere, and they're not really greenhouse gases. Now, this is a reaction whose kinetics can be studied rather easily. So let's say we wanted to discover what kind of reaction this is. We might compare some data. So the first kind of data that we could compare is comparing the initial concentration of N2O gas to the rate of its consumption, and that we write as dN2O over dt, or sorry, negative dN2O over dt. Again, we're comparing the initial concentration of our reactant, N2O, nitrous oxide, laughing gas, to the rate of its consumption. So if we had this kind of data and we were to plot it onto this graph, we would get a nice straight line like this. And so if we were to get this straight line from comparing the initial concentration to the rate of consumption, this is consistent with first order kinetics, or this, we could say this is a first order reaction. So this isn't the only type of data that we might be given on the consumption of N2O gas. We might also be given a table of the concentrations of N2O and the times associated with them. So if we were to sort of monitor the reaction progress, we could sort of notice a pattern in the rate at which N2O gas is consumed. So again, we could plot this data onto a graph, and this time we would be comparing the time that has passed to the concentration of N2O gas. So if we were to do this, we would get a curve something like this. So this isn't actually particularly useful, and the way we can actually make it more useful is by taking the natural log of the concentration of N2O gas. And so again, I'm going to redraw this plot here. So this time we're comparing the natural log of the concentration of N2O gas to the time that has passed. Now if we were to do this, we would get a line that looks like this. And so if we get a straight line from comparing the natural log of N2O gas, or the natural log of our reactant really, to the time that has passed, this is also consistent with first order kinetics. And not only that, but we can also find that the slope of this line is equal to the negative of our rate constant or reaction constant K. So two pieces of information, and these are two different ways that we could determine that this is a first order reaction based on experimental data. Again, the first is comparing the rate of consumption to the initial amount of our reactant, and if we get a straight line for that, that's first order. And then the second way is if we compare the natural log of the concentration to time and get a straight line from that, we would find that that is also consistent with first order kinetics or a first order reaction. So now that we know that this is a first order reaction, we can write some of the rate laws associated with this. So the first is our differential rate law. So our differential rate law says that our rate, negative d concentration of N2O over dt, again this is how we write the rate of consumption of N2O in this case, or just the rate of the reaction, is equal to K, the reaction constant K, times the concentration of N2O gas to the first power. And again, because the exponent here is 1, or the sum of exponents I should say is 1, this is also consistent with first order reactions. So this is our differential rate law. And then we also have an integrated rate law. And our integrated rate law says the natural log of the concentration of N2O gas at some time t is equal to negative k, our rate constant, times the time t that has passed. Now this is the same time associated with this concentration, that's why I said N2O sub t, plus the natural log of the initial concentration of N2O gas, which here I'm designating as N2O sub 0. So these are the two rate laws associated with first order reactions, and I've written them out for this specific reaction. And then we have one more sort of important equation associated with reaction rates and rate laws, and that is our half-life. And just as a reminder, half-life is often abbreviated as T1/2, and that's defined as the time at which the concentration of N2O gas at that T1/2 is equal to 1/2 of the initial concentration of N2O gas, or our reactant. So if we want to find an expression for the half-life, what we would do is we could plug these values into our equation here. So the time and we're going to plug them into our integrated rate law. So the time goes into, the half-life time goes into this T slot here, and then the concentration of N2O gas associated with that time is this N2O sub T1/2. So we're going to plug that in here, and what we get from all of this is that the natural log of concentration of N2O gas at the half-life T1/2 is equal to negative K times T1/2 plus the initial concentration of, plus the natural log of the initial concentration of N2O gas. And so now what I'll do is I will substitute in our little expression for the concentration of N2O gas at our half-life. So that will say natural log of 1/2 of the initial concentration of N2O gas is equal to negative K times our half-life T1/2 plus the natural log of the initial concentration of N2O gas. And so what I'll first do is I'll bring all the things with the natural log over to the left side of the equation. So we get the natural log of 1/2 our initial concentration of N2O gas minus the natural log of the initial concentration of N2O gas is equal to negative K times T1/2. So I'm going to use logarithm rules to combine the two things inside the natural log here. So the way that we do that is we say the natural log of 1/2 the concentration of N2O gas initially divided by the initial concentration of N2O gas is equal to negative K times the half-life, T1/2. And so what we can do here is a nice little trick where we cross out the initial concentration of N2O gas because it appears both in the top and bottom of this fraction here. So we get the natural log of 1/2 is equal to negative K times T1/2. And solving for T1/2, we get that the half-life, and solving for T1/2, which again is our half-life, we get T1/2 equals the natural log of 2 over K, the rate constant. And the natural log of 2 is about equal to 0.693. So if you sort of need a quick and fast way to calculate the half-life, it's about equal to 0.693 over K. And that is our half-life equation. And so what this tells us is that the half-life of this reaction doesn't actually depend on the concentration of N2O gas. It is only dependent on the rate constant K, which is specific to each reaction at a given temperature. And again, this is our half-life equation and the approximation. And then we have our integrated rate law equation. And finally, we have our differential rate law equation. And these are the big three equations associated with first-order reactions.